So non-differentiability essentially means that the derivative does not exist at a specific point. Every example I've had you guys look at until right now, everything has been differentiable. We haven't had any points of non-differentiability. So this graph, I will say, the point of non-differentiability might be sticking out like a sore thumb. There's one place on this graph where the function's derivative, or m prime, would not be defined. And if you're wondering, is it where x equals 4? That is correct. This is the spot, I would say, a couple things. I'm going to pause and write a couple things down here. If you need to pause and write that down, you can. What I just wrote down basically was non-differentiability means m prime is not defined at a specific value. And for this graph, m prime of 4 does not exist. It's a place of non-differentiability. Now, how I can look at the graph and tell is if I see a sharp corner, I see a cusp, that's a place where the derivative does not exist. That's a point of non-differentiability. Why? Here is why. When we talk about the derivative, we are talking about the slopes of tangent lines. So I do want you to try to picture some motion here. Picture things moving around on the graph. And if we think about the graph of m of x, and I'm going to just take a couple points. I'm going to draw some points that are getting progressively closer to the point that I'm claiming is non-differentiable. So if you can picture the tangent line at each of these points, it's like a steep line, and it's going to get more and more steep, but it's positive, you know? It's a positive slope. So as I approach this point 4 from the left side, as I get closer and closer to 4 from the left side, I'm getting a tangent line that is getting to be more and more positive, whatever. But as I approach 4 from the other side, the right side, here is a tangent line that's got a negative slope. That's a downhill slope. As I get closer to 4, it's a downhill slope. As I get closer to 4, less downhill, but still downhill. But the point is, this right at 4, it's not a smooth transition. Like, if this were a roller coaster, right? And you were in a roller coaster car and you hit this part, there'd be a moment up here where like your roller coaster car will be teetering and tottering because that tangent line at that point is not defined. Contrast that with the point over here at 3, where as I get closer to -3, that derivative starts off as positive and it's less positive and it's less positive. As I approach -3 from the right side, it's negative, it's less negative, it's less negative. But right here at -3, it's like a nice smooth transition that's going to equal 0. That doesn't happen when we have sharp corners. If you're looking at that sharp corner, the tangent line just before 4, the one that would be here, and the tangent line that's just after 4, man, they're very radically different tangent lines, and it doesn't simply just kind of like smoothly transition to the other. It's like we're going positive, and then it like ka-chunk, and just becomes super duper negative. So we can't, if I were to zoom in on this specific point, you wouldn't see that nice straight line that we saw when we started all this stuff a couple months ago. It would just be a sharp point. So what I want you to understand about this right now is graphically, if you see a sharp corner, if you see a cusp, which is like this, or a corner, which is like this, that's a point of non-differentiability. And it just means the derivative is not defined there. Nothing major. Non-differentiability means derivative is not defined at that point, means you have a sharp corner or a cusp. A question that came up in class that I wanted to address actually too. It's definitely the case that if you have a corner or a cusp, it's non-differentiable. Definitely. But there are also times where you can have non-differentiable points that are not corners or cusps. Not in the graphs I'm going to give you right now, you know. So if I'm asking you right now to identify non-differentiability and all I give you is a picture and nothing else, you're just looking for corners and cusps. Later on, when we do more stuff with functions and things like that, there'll be other ways to say, non-differentiable there, and here's why, and we'll talk about that later. So corners and cusps are not the whole picture, but definitely, for sure, you can always say, if there's a corner or a cusp, you can definitely say that's a point of non-differentiability, and the derivative, the first derivative there, does not exist. That's all I wanted to say about that.